This is more two, part A. We're going to be deriving the 3D heat diffusion equation uh, for Cartesian coordinates. Um, so, right, we have this cube here. We're going to be going across this cube. So first we want to define our directions. So if we draw we have our x direction here, and this will be our z direction. And then going into the page will be our y direction. And so that on this cube will make this x, this dx, this is y, over here is dy, that's a z, dy, here will be z, and up here will be dz. So to get the 3D heat diffusion equation, we have to first look at our energy. And so in this block, energy is going to be stored. So we can write our energy storage equation, which is going to be rho CT dt, right? Because that relates our temperature to our heat capacity, but then you have to include density because heat capacity brings in kilograms. And then we want it across the volume. So we have our dx, our dy, and our dz. Next, we want to look at the energy generation, right? So Eg, that's going to equal our heat flow. And then again, throughout the volume here, 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 and here. So it's going to be, again, a dx, dy, and dz. And so from this, we're going to start looking at a Taylor series expansion, right? So like a Taylor series expansion, you have a slope with a known point x. You know the slope of this. Let's say it's df dx. You want to know this point up here. We'll call this x naught. What you'll do is linearization, and you'll get your point up there because you know this point here, right? So that will look like dx naught is similar to dx plus d df dx evaluated where x naught, right, that's our second point, is equal to our first point, and then times the change in our position, right? So that's just going to be x naught minus x. And using this, we can then relate x naught to dx. And so what we're going to do with this is we're going to look for our change across our volume here, right? So we're going to go from x to dx. And so for this, we're just going to plug in, right? So we want to know dx, and that is about x plus d dx, dq dx, sorry, evaluated at dx equals x from dx to x, right? And so we know that in our system, right, it's going to be q equals q dx minus qx, right? That's or that's not q, that's our net heat flow for x, right? And we know this because it's just out minus in. Nope, this is actually incorrect. It is qx minus q dx, and it's in minus out, right? And so when we plug this in, right, so we have our qx, right, minus, and then we can plug this in. So it will be qx, right, plus dq dx, dx equals x from one spot to the other. Right, so this is, there's a parentheses here, right? So these two terms will cancel out, and that will then leave us for the net heat flow of x equals minus dq dx, evaluated dx, times the change in position, and we're at the corner, which will be defined as 0. Right, so this is our net heat flow for the direct x direction. And so when we look at our energy storage equation, it can be written as our energy generation plus the net heat flow in the x direction plus the net heat flow in the y direction plus the net heat flow in the z direction. So when we're looking at this, we have our equation for E gen up here, right? And then we just found this NHF at x, right? That's our net heat flow in the x direction. The net heat flow for y and z are found the exact same way, right? So we look at Q dy is similar to QY, dq dy, evaluated from dy where it equals y, dy minus y, right? And this is exactly the same as what we had up here, just now it's in the y direction, and we can follow the same path that we did here. We can get our net heat flow for y to equal minus dq dy, evaluated dy equals y dy, right? And so that can be repeated a third time for z. I won't go out and do that, but it is just minus dq dz, evaluated dz equals z dz, right? So these are all basically the same, just throughout the different directions. So when we look at this, right, we can plug in our equation for energy storage, right? So rho c t over dt, dx, dy, and dz equals our energy generation, which from before was just q dx, dy, dz. And then we can plug in all three of these, right? So it's going to be minus dq dx. And here we're just going to bring this up here, right? And so it's dq dx dx minus dq dy dy. And then finally in the z direction, right? So this is your overall equation right here. And we're going to use this along with Fourier's law. So I'm just going to copy this real quick and bring it over to a new page. All right. So we know that Fourier's law, right, is Qx equals minus K A dt dx, right? And what we can do here is we can look at this A, and when we go into for the volume, right, in the x direction, right, we're going along this way, and so our cross-sectional area is going to be this this side, right? So it's going to be our dz and our dy, right? So we can go into this equation, all right, qx equals minus k dy dz dt dx, right? And from this, right, we can do the same thing for the other equation. So we know that qy, right, it's going to be this face, and then dz will be this face, right? And so when we go into here, we have minus k, and then dx dz dt dy, and then in the z direction, minus k dy dz dt dy, or dz, right? And so we have now all three of our q's. And so we can plug these into our equations respectively here, here, and here. And so when we do that, we get the new equation, rho c t dt dx dy and dz equals our energy generation q dx dy dz. And then we can plug all of these in, right? So we have plus, and then it'll be minus d dx times minus k dy dz dt dx, right? Plus the y direction minus dy ddy minus k dx dz dt dy. Oh, this should be an x, sorry. And this is dy. And then our z direction, of course, the exact same, d dz minus k dx. Ooh, I'm going to rewrite this a little bit smaller. Minus d d z minus k dx dy dt dy. Nope, dt dz, sorry. Right, and so when we're looking at this overall equation, there are a couple of things to note. Right, every single term has a dx, dy, and dz. And I actually did not write it on these ones, but this has a dx, a dy, and a dz, right? So from each of these, all right, we can cancel these terms. And so that gets rid of our volume terms throughout the equation, right? So what we're left with is rho ct dt equals q plus minus d dx. And what we're going to do here is we're going to factor out our k from each term, right? And so when we factor out our k, we get q minus k times d dx dt dx minus d dy dt dy minus d dz dt dz, right? And so what we're going to do here, we're going to divide out our rho c, right? Because our goal here is to get to our dt dt, right? That's our change in temperature over our change in time. And when we divide out, we get q over rho c, then minus k over rho c times our term here, which I will just copy down. Right? So we have this. Now, if we remember from the first homework and our lectures, we know that this K over rho C, that's our thermal diffusivity, right? So overall, that will simplify that down. And then we can notice that each of these will be second derivatives, right? So we can get to our final equation of dt dt equals our thermal diffusivity times our second derivative of temperature with respect to x. We're going to factor out our negative, right? So then our second derivative of temperature with respect to x plus our plus second derivative of our temperature with respect to y, plus our second derivative with respect to z, plus our q over rho c. And so this dt equation is our final expression where the change in temperature over time equals the thermal diffusivity times the second derivative of temperature in all three directions times our heat, or plus our heat flow over our density times our heat capacity. And so this will be our three-dimensional heat diffusion equation in Cartesian coordinates. And if you recall, this is very similar to our 2D heat diffusion equation that we derived earlier. Recording in progress. From this, we're going to move on to an example, right? So if we look at, say, a tube here, right, we have, right, one side is going to be 20 degrees Celsius, right? Air is coming up, right? It'll be a length L at 0 to L. And this will be our positive x direction. And this side is perfectly insulated. Right, we have our Q. So if we take our equation from before, in our example, it is just one dimension, right? So we can just take one dimension here. So we have our dt equals d squared t over dx, right? That's our one dimension. We don't need the y or the z, times our q over rho c, right? Or plus q over rho c, right? That is just removing these two terms from our equation. And then from there, we're going to relate this to Fourier's law. I know, surprising, but so Fourier's law, right? We have our Q equals minus Ka dt dx, right? And so in this occasion, we know, right? So it's going to be 80 over here. We know that heat is flowing in this direction, so our Q will be negative, right? And so when we look at this, it'll be Q times our volume, right? LA equals minus Ka dt dx. So when we're looking at the slope, right, we expect it to be perfectly flat over here because this side is perfectly insulated, right? So if this side perfectly insulated, we expect the slope here to be 0, and it'll gradually go down. So this is what our slope will look like in the throughout this tube here. And so the question is, why does it get so steep in this section here? So when we look at this, right, we know it's negative, right? So it's going in this direction, right? And we know that this is increasing, right? Our negative q is increasing. That's why it's going down and going into that direction. And so to counteract that increase, something on this side has to increase. Well, our Ka is not going to increase, right? That's our thermal conductivity times our area. That's not changing, right? We know this isn't changing either, right? That area is not changing. So this has to be increasing. And so as our slope increases, our negative q increases, so it gets steeper, right? Also, our L is increasing, right? So as you move along, it's going to be a smaller and smaller L, so our slope is going to be smaller and smaller, right? So this increase in slope that is required by the increase in our negative q is the reason for our slope becoming so steep at the end of this tube here, right? So we started at our 0, and as our q increases, our slope has to increase to keep this equation balanced, right? So next we're going to look at a grid here. I should have drawn this out before, but I did not. So if we look at this grid here, I'm going to draw this out real quick. So, right, we can look at this grid. So we will have our x direction going this way and our y direction going this way, right? And then on this side of the grid, it's going to be 100 degrees Celsius. Over here, it'll be 200. Up here, it'll be 310. And down here, it'll be 250, right? When we're looking at this, this section here will be our delta x, and this will be delta y. So what we now have here is 2 dimensions, right? So if we take our equation from before, if I can copy it, so we have our equation from before here, right? We don't need this z term anymore, right? Because we only have our x and our y, right? So that's going to go away. And then in the problem, we're given that there's no energy generation. Well, this is our energy generation term. So now this term goes away. Great. That just simplified the problem a whole lot more. So now we're down to dt equals our thermal diffusivity times the second derivative of temperature in the x plus second derivative of temperature in the y, right? Also in the problem, it says that it's steady state. What is steady state? This is going to go to 0, right? So now we're at 0 equals our thermal diffusivity times the second derivative of temperature in both the x and the y direction, right? Now, to make the problem going forward a little easier, I'm going to keep this dt here, dt, just so it's a little easier to see everything that I'm doing. So we're going to work with this equation here, right? this is our simplified 3D, our 3D heat diffusion equation. It's now 2D. Now this is our 2D heat diffusion equation at steady state with no energy generation. This is the part of the question this is the first part of the question that it asks for, right? We know steady state means there's no change in temperature with time, and no heat generation. We know that Q over rho C has to go to 0. So when we look at this problem here, let's say we're looking at a square in the position I and j, right? We have to have a couple of equations here, right? So for time, at any time, right, there's the time you're at times the change in time. That equals time. We do that for the x direction, right? So x equals I, right, which is any position times your change in position. And we do the same thing with j and y. So when we go here, we have our temperature at ij. And then we can look around it, right? We have our temperature at I plus 1 j. We have our temperature at I minus 1 j. Our temperature at I j minus 1. And then our temperature at I j plus 1, right? So that is what's around our that's what's around our temperature that we're looking at. So how does this break down into what we need, right? So the change in temperature and change in time. So at any temperature, right, I in the x direction, right? So so at any temperature I j, right? That's just our normal thing. How does it change with time, right? So we look at our n plus 1, right? That's our n from this equation here. That's any variation in time. And then minus our temperature at ij at n. And that all is with respect to the change in time, right? So when we're looking at this, we can move on to this side of the equation, right? We have our thermal diffusivity. And so what is the second derivative of temperature, right? We're going to have our change in temperature, right? So it's going to be T in the x direction, Ti plus 1 j minus Tij, right? That's our current position over the change in x, right? And then minus, right, our change in position our current position ij minus Ti minus 1 j. And that's also over our change in x, right? And since it's a second derivative, we know that we have to have a second delta x down here. Then we can repeat this for our y. We have our t, and these all are with respect to time. Our t I j plus 1 minus our t I j, right, over delta y minus our t I j minus our temperature at a change in position downward, right, over our change in y. And then still second derivative, so it's another delta y. So when we're looking at this, we can simplify this down a little bit. We're going to go up here. And so we'll take this. This does not change. This section here does not change. So we'll copy this. And then that will equal, what we'll do here is we will bring all this down. So it's T I plus 1 j minus ti minus 1 j minus 2 tij over delta x squared. Right. And then we can do the same thing for the y direction. Tij plus 1 minus tij minus 1 minus 2 tij over delta y squared. Now, from this, we are going to assume that delta x and delta y are the same, right? I know that I didn't draw it perfectly, but delta x and delta y are intended to be the same. So from that, we can rewrite this as ti plus 1 j minus ti minus 1 j plus tij plus 1 minus tij minus 1 plus 4 tij over, and so how we'll do this is we'll call delta x and delta y, right? Those are going to be the same. We'll just call them delta, right? So it's over delta squared. Now, when we do this, this is still equal here, right? So tij n plus 1 minus tij n over delta t. We can then take out, right, these terms here are going to cancel our tij tij over delta t, right? So we come out with a final equation of tij n plus 1 equals t, our temperature, I plus 1 times j minus ti minus 1 j minus tij minus 1, sorry, tij plus 1 minus tij minus 1 all over 4. Right? And so we look at this. Actually, this is plus, and this is also plus, right? But when we look at this, we notice, right, we have I plus 1, I minus 1, right? I plus 1, I minus 1, j plus 1, j minus 1, all over 4. So really, all tij is the average, right? And that's what we kind of expect when looking at what Ti is, right? We want the average of the temperatures around it, right? So to further show this, I'm going to map it out in Excel. And so we will do that now.
Okay. So I pulled up our Excel file here, and then I have my problem that I did just right before this. And so we're going to do that grid problem in Excel, right? So from the problem, we remember that we had our T left, right? That equaled 100 degrees Celsius. Our T right equaled 200 degrees Celsius. Our T top equaled 310 degrees Celsius. And then our T bottom, that was 250 degrees Celsius, right? So we're going to make this, we are going to make this our equations, right? And then we are going to make a grid, right? So we'll start here. We'll have our T left. And I got to put an equal sign. Right, we'll bring this down, let's say, sure, this many. Great. And then we'll have our T top. Again, equal sign. We will bring this over to about here. We will have our T left, or our T right, sorry. Bring that down. And then we will have our T bottom. Um, and then we will bring this over to here. Right, so now we're looking at a grid, right? And so when we look at our equation, right, we had from before um, Tij equals Ti plus 1j plus Ti minus 1j plus Ti plus or plus Tij plus 1 plus Tij minus 1 all over 4. So how are we going to do that in Excel, right? So we will have, right, our we determined that it was just the average of what's around it, right? So we'll have our right value plus our left value plus our top value plus our bottom value, all divided by 4, right? And then we will bring this calculation all the way down and then all the way over. Uh, so when we do this, we get our grid of values. Now, if you are doing this, this might not work. It might be a circular reference. So what you'll do is you'll go down and go to options, go to formulas, and you'll enable iterative calculations, go up to 10,000 to get more accurate values. And so when you do that, you get this grid here, which shows your temperatures using the equation that we found in the third part of the question, right? So that is how you do this part of the problem.